Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 9, Atomic Structure, Part 2. Here are our objectives for today's video. Pause here. The last video, we talked a little bit about the dual properties of light, how while light is primarily treated as a wave, there are times in which we treat it as the particle. And the same also applies to particles. Every particle has some wave-like properties. Some have more wave-like properties than others. There's something called the de Broglie wavelength that can actually give you a mathematical relationship between the two. We're not really going to spend too much time with it. It's a little bit beyond the scope of the course. But what you may want to glean from that is that things that have extremely low mass, like electrons, are more likely to have more wave-like properties. And when I'm saying wave-like properties, I specifically mean indefinite location, though there are other applications of it. But the way that will be most useful to you to think about will be to think about it in terms of indefinite location. Pause here. So as we talk about electrons, they're going to have fundamentally different properties than, say, a baseball or something like that. And one of these different properties of these objects that are so small that they have more wave-like properties is something called quantization, where changes in certain properties, such as energy, can only occur at discrete values. And when I say discrete values, I mean that, let's just say at around 1.527 times 10 to the negative 19th joules, that will cause an electron to jump from one energy level to another. But there's not a continuum. It has to be exactly that, like a light switch. If something is not quantized, so pretty much everything about like macroscopic objects is not quantized. Those values are continuous. So like the energy, the kinetic energy of, say, a car, that's continuous. It can be any value. Whereas the energy that is absorbed by an electron, that's not. That's quantized. It can only occur at discrete values. Pause here. All right. So this equation here only applies to electrons in a hydrogen atom. And what this can do is we can predict the energy that will cause an electron to transition from one energy level to another. So you may remember seeing a model of an atom before where there were distinctive layers where the electrons were. The first circle around the nucleus, that would be n is equal to 1. The second circle would be n is equal to 2, and so on and so forth. We can predict what the change in energy between the levels is using this equation right here. And then we can translate that to the wavelength and frequency of the light that will cause that transition. Pause here. Okay, I'll take a moment to work through this. So if you didn't already know this, the triangle in front, that's called a delta. It just means change. It's not really going to affect what we do with this particular type of problem. So then the question says that it's changing from n is equal to 1 to n is equal to 2. So that means my final is 2. Put this in my calculator and I got 1.634. I just went with the number of sig figs. It was in 2.178, but this is not really a type of problem that I would be strict on sig figs for, because this is really a theoretical construct anyway. Pause here. So then from here, even though there is the delta, the triangle in front of it, we can still use the equation E is equal to HV and just solve for V to get the frequency. Then we just plug in what we just got and divide it by H. And then remember to include units. And then for the second one, I use lambda V equals Z. just plug in what I got for the prior answer. And these orders of magnitude look like things I've seen before, and that's because these are both on the electromagnetic spectrum, which gives this just some interesting properties. All right, that's all for tonight's video. Thank you so much for watching, and have a great night.